Welcome to the lecture series of Mathematical Modeling of Manufacturing Processes with subject code KME 073. I am Dr. Suman Gotwal, working as an assistant professor in the Department of Mechanical Engineering at AKGEC Engineering College, Ghaziabad. So in today's lecture, we are going to discuss about the mechanics of bulk metal forming. So these will be the outline of today's lecture. First, we are going to discuss about the forging. Forging is the part of the bulk metal forming processes, means it is one of the bulk metal forming process. We will do the analysis of the forming process, and there are some assumptions which are made during the analysis. So we will see what are those assumptions. Then we will discuss the analysis of a slab. So workpiece will be in the form of the slab, and we will discuss the it in the plane strain compression condition. So there are three types of conditions here. First one is slipping friction, second is sticking friction, and the third one is the combination of the slipping and sticking friction. So we will discuss all these three conditions or situations in detail in coming slides. So first we will discuss about the forging, means what is forging process. So forging is basically a manufacturing process in which the material is deformed plastically to give the proper shape and size. So how the shaping of the metal is done? The shaping of the metal is done by applying the external force, which will plastically deform the material, and this force can be applied with the help of the hammer, with the help of the presses, means in case of the large work pieces we use the presses to apply the force on the work material, or we can use the rollers also. These compressive forces, now in forging, the forces, the type of forces that which are involved are the compressive in nature. So these compressive forces are delivered with a hammer or die. We can use the die also, that can be the open die forging or the closed die forging. The workpiece is compressed between the two dies containing the shape contours. Okay? So die is divided into two halves, okay, and the internal surface of the die is having the final product contour. So the product will take the shape of that contour which is on the die when it will be compressed between the two halves of the die. Okay. The forging is often categorized according to the temperature. So we can do the forging process at different temperature, and as per the temperature which is involved in this process, we can categorize it as the cold forging, warm forging, or the hot forging. Okay. So here you can see that the work material is heated and the hammer is used to apply the external force to give it proper shape and size. Now the forging analysis. So as I have discussed that in case of the forging, the material is compressed or forged between the two halves of the die, and during this process, during this compression, the plastic flow of the material will takes place. It means there will be continuous change in the shape and size of the material, and during this process the stress and strain at a point will also change. Okay. So this analysis is basically done to represent the instantaneous conditions, means what will be the deformation at what force. Okay. So this analysis is the case of the open die forging. So some assumptions are made for this analysis for the simplification purpose. So first assumption is forming process in which the metal is compressed or entire forging is plastic in nature, and the plane sections before the deformation remains plane during the deformation, means plane section will remain plane during the deformation also. The condition for plastic flow is considered for the entire workpiece. Okay, and the length of the workpiece is much more than the width, and the problem is plane strain type. The width which is considered to be in the direction perpendicular to the plane of paper. So जो width है, width is at in the direction which is perpendicular to the plane of paper. The coefficient of friction is taken as a constant, and the material is rigid, perfectly plastic in nature, and effect of strain hardening and strain are neglected here. So these are the assumptions. Now we are going to discuss the analysis in the plane strain compression. So first we are going to discuss about the compression with the column friction. So in case of the column friction, basically the frictional force which is acting between the die and the workpiece interface surface is proportional to the normal pressure. Okay, so F is basically the frictional force here. We can take this as the tau. ठीक है, फ्रिक्शनल जो है यहाँ पे फ्रिक्शनल फोर्स हो गया, एंड दिस इज प्रोपोर्शनल टू द प्रेशर P. It is proportional to the P. So we can say here F is equal to mu P. So mu is basically the coefficient of friction, and during the assumptions we have taken it as a constant. Okay. These conditions may exist when the forming tools are well lubricated and compression is done at the ambient temperature. So in this particular case, all the tools which are involved during these operations are lubricated, and this process is done at the ambient temperature. This is the case. This case is basically known as the slipping friction. Okay, so first we are discussing about the slipping friction situation. So here in this diagram we can see that this is our workpiece which is in the form of a slab, rectangular slab is there, and this is the die, two halves of the die. This is the top part and this is the bottom part. Okay, this is the center of the workpiece. So complete jo length that is the 2L, but we are taking a half of the length, that is L. And we are first analyzing a particular section, and we can see here that its thickness is equal to dx. dx hai, and it is at a distance of x from the center. Here the lateral stresses sigma x and sigma x plus d sigma x are acting on the vertical surfaces, and this px is basically the die pressure. So top die is exerting a pressure which is equal to px in the downward direction, and this is this bottom die is also exerting a pressure on the workpiece. So it is compressive in nature. So now you can see here the tau x is also acting here, or we can say Fx is also acting here. So this is the frictional force which will be in the opposite direction. Okay, which will be in the opposite direction to the plastic flow. So this Fx is at the interface of the die and the workpiece. So here we can see here that the stresses which are acting on the faces of the slab are Px is basically the die pressure, Fx is the frictional stress at the die material interface, sigma x and sigma x plus dx are the lateral stresses which are acting on the vertical surface of the slab, and L is half of the width of the strip. Okay, and B is the dimension of the strip which is perpendicular to the paper. This is basically the width. Okay, and this is the length. H is basically the thickness of the strip. The equilibrium of forces which are acting on the slab in the x direction will be, we have already seen here that in x direction these two forces are acting and Fx is also acting. So we can write down the equilibrium equation of forces sigma x plus d sigma x into h into b, means thickness into width, minus, because these are in opposite direction, minus sigma x into h into b minus 2 into Fx, because the Fx force, frictional force, is acting along the top die and the bottom die. So we have taken here 2. 2 into fx dx into b is equal to 0. This is equation 1. Now we will simplify it. So we will get this equation. Okay, we will get this equation. If we divide this equation with h into b into dx, then we will get d sigma x by dx is equal to 2 into fx by h. So as per the column friction, fx is equal to mu px. So we will substitute this value in this particular equation. So this equation will become d sigma x by dx is equal to 2 mu into px divided by h. And this sigma x and px are basically the principal stresses, and the process is in the plane strain compression, and we are working with the von Mises hypothesis of yielding. So if sigma 1, so three principal axes, if we talk about the three principal axes, if sigma 1 is equal to sigma x, sigma 2 is equal to px, sigma 3 will become half of sigma x minus px. This is equation 4. Now, in terms of the von Mises criteria, we can write down the principal stresses as sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 6 tau y square. Okay, so we will put the value of sigma 1, sigma 2 and sigma 3 in equation 5. Okay, so when we put the value and we solve this particular equation, then we will get sigma x plus px is equal to 2 into sigma y by under root 3. Okay, and from the von Mises criteria, we have seen that sigma y by under root 3 is equal to k. So we can write down sigma x plus px is equal to 2k. And for the simplification purpose, we can take this complete term 2 into sigma y by under root 3 as the sigma naught dash. Okay, so sigma y is basically the yield strength of the material in the tension or the compression. Okay, so we will write down this particular equation as sigma x plus px is equal to sigma naught dash. Okay, this will become equation 6. Now, if we differentiate this equation, then we will get d sigma x plus dpx is equal to 0. Okay, so we can write down d sigma x is equal to minus dpx. This will become equation number 7. Now, from equation 3 was, this is our equation 3, d sigma x by dx is equal to 2 mu px by h. So here we will put the value of sigma x, which comes out to be minus px. So d sigma x is equal to minus dpx by dx and 2 mu px by h. Now we want to find out the value of the px. Px is a die pressure. Okay, so we will rearrange this particular equation. So it will become dpx px is equal to minus 2 mu by h into dx. If we integrate this equation number 8, then we will get log of px is equal to minus 2 mu x by h plus c. Now, c is basically the constant of integration and which can be determined from the stress condition at the edge of the strip. So, at the edge of the strip, x will become L, x will be equal to L and sigma x will become 0. Okay. So, and we if sigma x becomes 0, then from equation 6, sigma x plus px was equal to sigma naught dash. Okay, so we will put the value of sigma x here. So we will get the equation, get the value of px. So px will become equal to sigma naught dash. Now if we put this value in equation number 9, equation number 9 is this one. So we will get the value of c. Okay. Here we will get the value of c. Now we will put this value of c in equation 9. Okay. Then we will get this log of px is equal to minus 2 mu x by h plus log of sigma naught dash plus 2 mu into L. If we rearrange this, then what we will get? So, after solving this, we will get the value of Px, that is die pressure. So, we can see here, this is the main factor on which the die pressure is dependent, or this is the factor on, which will affect the die pressure. Okay. So, this is the die pressure that we get after solving the equation. So, this is the main factor. Now, this was on the right hand side of the strip, but similar expression we can obtain for the left hand side of the strip also. Now, if we want to find out the total die pressure, so we can find out the total die pressure if we integrate Px, if we integrate this die pressure over the interface area which is between the die and the workpiece. So, it will become PT will become 2 into B. B is the width of the workpiece. 2 into B 0 to L. Okay, 0 to L Px. Okay, so it will become like this. So, we will get the PT here. Okay. Now, what we will do? This is the total pressure. Now, if we want to find out the mean pressure or average pressure, mean average pressure, then we can find out it as Pm will become equal to, if we divide the PT total die pressure by the area of contact, 2 into L into P. So, we will get the value of Pm here, average die pressure. Okay. Now, here the plot of die pressure for different values of mu is shown. So, we know that the die pressure in the slipping conditions comes out to be sigma naught dash e to the power 2 mu h L minus x. So, this is the pressure distribution of die in the plane strain compression condition. So, we can see here that if the value of x is 0, value of x will be 0 at the center of the workpiece. So, if x is 0, then pressure will be maximum. Px will become sigma naught dash e to the power 2 mu L by h. Okay, pressure will be maximum, but at the edge of the workpiece, means when the x is equal to L, then pressure will be minimum. Px will become sigma naught dash. So, at the edge of the this, we can see here that the pressure is, die pressure is equal to sigma naught dash. So, this is the value of mu, means it is also depending on the mu, value of mu. As the value of mu will increase, the die pressure towards the center will also increase. So, we can plot the die pressure along the different values of mu. Mu1 is 0 here, mu2 is greater than mu1, mu3 is greater than mu2, and mu4 is greater than mu3. And here we can see here the relationship is not linear. So, we are getting this type of curve here. Okay. Now, we will see the compression with the sticking friction. So, sticking friction. So, now we will discuss the compression with the sticking friction. So, in case of the hot forging, where the temperature is high, then the coefficient of friction will also be high. And this is the situation where the no lubricant or very little lubricant is used. So in this case, basically the layer of material which is contacting the die surface may stick in onto the die, and the flow will takes place under the surface layer, and this particular condition or situation is known as the sticking friction. Okay, so in many cases it may also happen that some portion of the workpiece is undergoing the slipping friction and another part is in the sticking friction. So in case of the sticking friction, basically the frictional stress on the interface will be equal to K. So here the Fx will become equal to K or tau y. Okay, so same diagram is used here for the analysis purpose. So we are using the same analysis. So from there we can take the equation number 2. So equation, as per the equation number 2, d sigma x by dx is equal to 2fx by h. So if we substitute the value of fx, which is equal to k, in this equation 2, then it will become d sigma x by dx is equal to 2 into k by h. So from equation 7, we know that the d sigma x is equal to minus dp x. So we will put the value of sigma x here. So we will get dpx by dx is equal to minus 2k by h. Okay, so we will rearrange this particular equation and it will become this. This is equation 15. If we integrate this equation, then we will get this particular equation, and if we want to find out the value of c, which is the constant of integration, then we can find out it as the edge of the strip. Means at the edge of the strip, basically x will become x will be equal to L and sigma x will become 0, and the value of px will become sigma naught dash. Okay, so we will put these values in this particular equation, which is the equation number 16, and we will get the value of c. This value of c we will put in the equation number 16, and we will get the value of px, which is the die pressure. So px, here we can see here, so that the px is this one. Now we can put the value of sigma naught dash also. So sigma naught dash is basically equal to 2k. So we will write down the sigma naught dash in the place of 2k. So this equation will become this, and after the simplification we will get the final value of the px. Okay, so here we can see there is a linear relationship in px and L minus x by h factor. Okay, we can find out the pt value also. So pt value will become basically 2p into 0 to L sigma naught dash 1 plus L minus x divided by h. Okay, from here we will get the value of pt. pt is basically total die pressure. So after solving this equation, we will get the final value of pt as 2 into b into sigma naught dash. Okay, and it will become L plus L square by 2h. Okay, this will become the value of pt. Now here the pressure distribution in the compression with the sticking friction is shown here. So we can we have already seen that at the edge of the workpiece we have the die pressure, which is equal to sigma naught dash. We can verify it from here that at x is equal to L, the die pressure will become sigma naught dash, and because there is a linear relationship, so we will get the straight lines here, and at the center of the workpiece we will get the maximum pressure, and at the center of the workpiece the x will become 0. So we will get the maximum pressure as sigma naught dash 1 plus L by h. Okay. The next is the compression with the slipping and sticking friction. Okay, so with the intermediate values of mu and suitable value ratio of L by H, both the slipping and sticking friction regions may be present on the interface between the die and the metal or the workpiece. Okay, as the interface pressure increases as we go from the edge of the workpiece to the center line. Okay, therefore the frictional stress, which is equal to mu px, will also increase. Okay, with high value of mu and high L by H ratio or both, the px may increase to a very high value and the frictional stress mu px may reach to k. You can see here there are two types of curve here. So first, Fx is frictional force is equal to mu px. Here this is the case of the slipping friction and this is the case of the sticking friction. Okay. The frictional stress on the right half is shown negative because the direction of frictional stress is opposite to that of the x. Okay, but in case of the left hand side, it is taken as positive because on this side the direction of friction is same as the positive direction of x, and this sticking is starting at a point where the magnitude of mu px will reach to a value which is equal to k. Okay, and we have assumed that the sticking is starting at a distance xs, which is from xs from the center. Now, we can find out the value of px, here. So, what we will do, as we know that F is equal to mu px. Okay, so mu px will become equal to k, or we can write down is equal to half sigma naught dash. Okay, from equation 10, we know that px is equal to sigma naught dash to e to the power 2 mu by h L minus x. So, it will become mu sigma naught dash e to the power 2 mu, if we put the value of this here. So, it will become by h L minus x is equal to k, or is equal to half of sigma naught dash. Okay. So, we can find out the value of, we can write it as the xs. Okay, क्योंकि sticking friction is considered here, so we are denoting it with the xs. After simplification, we will get the value of xx, which comes out to be L minus h by 2 mu log of 1 by 2 mu. Okay, so if we see the equation number 14 and we want to find out the equation number 16 and we want to find out the value of C, then we will take the boundary conditions, means x is equal to xs and px is equal to k by mu. So, if we will put, we will get the value of C as okay, and from equation 16 we will put the value of C. So, we will get the value of px as k by mu plus 2k by h xs minus x. Okay, this will be the value of the die pressure. Now, we can find out the total die pressure by integrating the px over the slipping and sticking friction. So, PT will become XX to L and 0 to L. Okay, because the sticking and sticking both are considered here, so we will get the value of PT as this one, and the average die pressure can be obtained by dividing the PT by area of contact, which is equal to 2BL. Okay, and Px will be obtained as XS is equal to 0, means at the center. So we can draw the pressure distribution in case of the sticking and slipping friction here. So these are the references. So thank you very much. That is all from my side for this lecture. Thank you so much.